Good morning. Welcome back to the video lecture series for simulation systems. This is Dr. P. Srinivasulu. Today we are going to discuss about Laplace. So in the previous videos, already we have discussed about the transforms, Fourier series and Fourier transform. Fourier series is applicable only for analyzing the periodic signals. Fourier transform is applicable only for analyzing the periodic signals and non-periodic signals. But in the non-periodic signals, it is not applicable for unstable signals. So that is the drawback of Fourier transform for analyzing non-periodic signals. In the non-periodic signal for unstable signals. So the Laplace transform is whatever the drawback in Fourier transform, that is overcome by up to some extent. So that is the only difference between Laplace transform and Fourier transform, because it is also analyzing for a continuous time signals and continuous time systems. So the main advantage of this Laplace transform is we can easily understand this Laplace transform compared with Fourier transform, and the systems also differential equations are for analyzing any system, or for analyzing the network concepts, or transient response analysis, or steady state analysis, and the network concepts. So these are all we can easily analyze by using this Laplace transform. So that is a main difference between Fourier transform and Laplace transform. And this Laplace transform is again split into two parts. One is a bilateral. Bilateral means two-sided. Two-sided means the time interval we are going to consider from minus infinity to plus infinity. Another one is unilateral. So unilateral means single-sided. It is like a practical cases. We are going to take from 0 to infinity time interval. So first of all, we will go with a bilateral Laplace transform, and wherever we require, then we will see this unilateral Laplace transform. Now observe the Fourier transform formula of Laplace transform. If you observe the Laplace transform formula, it is almost like your Fourier transform formula. Now, if you see already we know Fourier transform f of omega there, that is the Fourier transform of f of t. Now here Laplace transform of f of t is f of s. Integral minus infinity to infinity f of t e power minus j omega t there. Here it is a e power minus st into dt. So one more point here. The Fourier transform is a special case for Laplace transform. So if you know the Laplace transform, we can easily obtain Fourier transform from this Laplace transform. That is a more convenient transform to analyze the continuous time signals or continuous time systems or differential equations. Laplace transform is a better choice. Then it is the Fourier transform, Laplace transform formula. Now here in this, you see a new term, S we are introducing. This S is equal to sigma plus j omega. Here S is equal to sigma plus j omega. Here sigma is a real part of S, omega is imaginary part of S. So you can, in the oftenly, we are going to write also real part of S, imaginary part of S in the S plane. There is another word also we are going to discuss here, ROC, region of convergence. So this word is not there in Fourier series and Fourier transform. That is the main difference between Fourier transform and Laplace transform. Next, suppose if you want to write a formula for unilateral. that is from 0 to infinity. The second formula here, f of s is equal to 0 to infinity f of t into e power minus st into dt. Now, there is a Fourier transform pair. F of t Fourier transform is f of s. F of s inverse Fourier transform is f of t. So, s is equal to this sigma plus j omega. Okay. Now, if you substitute this, yes, sigma plus j omega. If you see the formula, f of s is equal to integral minus infinity to plus infinity f of t into e power minus sigma t into e power minus j omega t into dt. Now, it is looks like a Fourier transform of f of t into e power minus sigma t. The Laplace transform of f of t is equal to a Fourier transform of f of t into e power minus sigma t. So, you observe here, we are rewriting this equation. It is f of t into e power minus sigma t is separated. Now, integral minus infinity plus infinity, this f of t e power minus sigma t into e power minus j omega t dt is equal to Fourier transform of f of t into e power minus sigma t. Now, it must be according to the Dirichlet conditions to obtain the Fourier transform. To obtain the Fourier transform, there must be some satisfies the Dirichlet conditions. So there is finite number of maxima and minima, finite number of peaks, and along with this, it must be an absolutely integrable within the interval from minus infinity to plus infinity. So if you see here, this Fourier transform of f of t into e power minus sigma t to obtain the existence of Fourier transform, nothing but here existence of Laplace transform. So from minus infinity to plus infinity, the magnitude of f of t into e power minus sigma t into dt must be less than infinity. So whenever there is a e power minus sigma t, dt is less than infinity, the sigma value here, it depends upon the range of values of sigma. Suppose sigma is again here negative, sigma is again here negative, it is not possible. Okay. So the range of values of sigma is very important here. Okay, now next, if you see the formula of inverse Laplace transform, f of t, nothing but inverse Laplace transform of f of s is equal to 1 divided by, in the Fourier transform, there is only 1 divided by 2 pi. Here it is a 1 divided by 2 pi j. Integral, there minus infinity to plus infinity. But here, s is a sigma plus j omega. So you can write here sigma minus omega j infinity to sigma plus j infinity. So that limits of omega minus infinity to plus infinity. But real value of sigma, we need to consider here. And f of s into e power st ds. So it is the Laplace transform by importance of sigma and importance of s. Now, if you observe this formula, whenever sigma is equal to 0, the formula is same as a Fourier transform. That is the Fourier transform we are saying a special case for Laplace transform. Whenever sigma is equal to 0, Fourier transform, Laplace transform, both are same. Okay. So the word ROC, whenever it is a unstable signal, again this Laplace transform up to certain range of values of sigma, it is okay. But after range of values of sigma, the Laplace transform also fail. Fourier transform completely fails, but Laplace transform up to certain range of values of sigma, it is okay. That's why it is a region of convergence. We are discussing about this region of convergence. Now, properties of Laplace transform. You see the properties of Laplace transform. As usual, linearity property. Oh, you know, what is the linearity? Linearity means it satisfies both superposition and homogeneity. Whenever the system or transform satisfies both superposition and homogeneity, then we can say that it satisfies linearity property. What is the superposition? You know, superposition. Whenever, if you consider two signals at a time, whatever the response we are getting, that is equal to, you apply individual inputs, you will get the individual response. So if we add the sum of individual responses is equal to the response of weighted sum of inputs. So it is the superposition concept. Homogeneity means just it is a scaling factor. Now, we see this f1 of t Laplace transform is f1 of s, f2 of t Laplace transform is f2 of s. Then you see the first case, Laplace transform of a into f1 of t plus a2 into f2 of t. This a1 and a2 for homogeneity scaling factor, you can assume like a, b, whatever it is. Now, we are applying at a time. We are applying both the inputs. F1 of t is one signal, F2 of t is another signal. That corresponding scaling for F1 of t a1, corresponding scaling for F2 of t a2. So, both the signals we are applying at a time. So, Laplace transform of a into f1 of t plus a2 into f2 of t is equal to a1 into f1 of s plus a2 into f2 of s. Now you see, what is this f1 of s? What is the a1 into f1 of s? Individual Laplace transform of a into f1 of t. What is the a2 into f2 of s? Individual Laplace transform of a2 into f2 of t. What is the Laplace transform of a1 f1 of t plus a2 f2 of t? It is at a time we are applying both the inputs. So that is the a difference between individual response and at a time we are applying. Now, you take the formula Laplace transform of a1 into f1 of t plus a2 into f2 of t is equal to integral minus infinity to plus infinity. Here he has explained about this unilateral concept, but we are going to consider for bilateral only. So from minus infinity to plus infinity, a1 into f1 of t plus a2 into f2 of t e power minus st into dt. Now after then, you separate the terms and you observe this one, integral minus infinity plus infinity f1 of t e power minus st is f1 of s plus a2 into f2 of s. So it is a linearity property. Next, another important property, shifting property. Shifting property. Okay, I'm going to stop this. I will continue next.